Hello everyone, my name is Anthony Shivkumar, and in today's video I am going to talk about how we can improve our PCB design for fabricating power MOSFETs and brushless DC motor drivers. Now, if you're designing a brushless DC motor driver, it's a mixed signal in the sense that it's got a high voltage side and it's got a low voltage side. And the reason why I have been wanting to do this video is because I have been struggling a little bit in making my brushless DC motor driver work properly. In the sense, I'm able to make it work, but over time the MOSFET keeps blowing up or something keeps malfunctioning on my PCB. And to address this issue, I wanted to really dive deep into understanding the physics, the principles behind signal integrity, power integrity, what makes, how do you design a good layout when you have a mixed signal on the board, which is, as I mentioned, high power and low power. You have data signal on the same PCB, as well as switching frequencies and switching components such as the MOSFET. And how do you design so that it's more reliable and less susceptible to failure? And problems that I kept facing was my MOSFETs eventually started to blow up in the sense they started to malfunction. It would cause tremendous heat. And this is with having a pre-driver. So why is this happening and what's causing this to happen? The circuit clearly was not working properly. And at times, I would get the motor spinning a little bit and then suddenly would stop. There would also be a damage to my low power side. And this is where I had, my microcontroller. And over time, there would be power that would be injected into the microcontroller and would damage the pins. And now I have a couple of microcontrollers that just stopped working. So there's damage to my low power, which is a microcontroller consumes much low power, much low voltage, and it was damaging my electronics. And I wanted to know, why is this happening? Then, of course, the motor is not spinning properly. Too much heat dissipation. Yeah, of course, when you're switching, it's going to generate heat. But it was generating heat not because it was not predictable heat dissipation. It was more like something is blowing up, something is going wrong. That's really what that I'm trying to address over here. It's the heat dissipation is a natural phenomena when you're having high speed switching MOSFETs. But this heat was dissipated probably because of a short circuit or something that was not supposed to happen and causing damage. And how do we address those problems? And of course, because of all of this, it's inefficient and a lot more. So that's what made me come up with bringing and doing some research as to how I can address this problem so I don't repeat the same mistakes again in the future. There's a long learning curve because we're dealing with electronics and signal integrity and power integrity. You also need to have the right tools, the right simulation, and all of those things I really do not necessarily have. So I was trying to, wing it based on some designs, based on some principles, based on some guidelines. And now I'm really spending some time to train myself and, more importantly, get the right tools so that I can debug this at a much earlier stage and understand what's really going on. But before we even get to that, I've really made some few guidelines based on the application notes that I've read, based on certain principles, based on just learning and reading a lot of books related to this subject. And what I firmly believe might be causing these issues, possibly, it's not necessarily true because I've not necessarily measured it perfectly. I don't have the measuring instruments yet to do this. I'm eventually going to invest in them. But the thing is, what I've realized might happen would be something called as ringing. Ringing would happen when there's trace discontinuity. In simple English is if I have a wire connected to, and there is a change in impedance, that would cause some form of discontinuity because the signal is basically constantly looking at what's the impedance or the voltage divided by current at that very specific instance. And if that changes, then it's going to cause something called as ringing or reflections. And if that's causing, and if there's too much ringing or too much reflection, it can create a false trigger of a MOSFET. And if it creates a false trigger of a MOSFET, when it's not supposed to be on, it's off. And when it's supposed to be or when it's supposed to be off, it's on. That's the kind of impact it can have. We'll talk a little bit more about ringing and trace discontinuity in another video, but that's possibly one reason. Then there could be ground bounce, in the sense that there is a voltage that is triggered onto due to a switching of one wire or one trace is causing the other trace to react to the signal happening. It's some form of crosstalk in that sense. And that's something that I'll talk a little bit more about how that happens, and it's mostly related to the amount of layers that you have on your PCB and how you can prevent ground bounce. Then there's of course crosstalk, in the sense that one signal from one trace is directly interacting with the signal on the other trace, and how we can prevent that. And a simple way to prevent crosstalk is to make sure that you have the wires are not close together, or the traces are not close together. There's a distance between them. I'm saying these are all possible causes, because this is just generally, when you study signal integrity, these are the kind of things you're basically trying to address. And there's parasitic capacitance, in the sense that there's capacitance that you're not modeled into the system, but it exists, and now you want to eliminate it. So every trace will have some form of an impedance, some form of inductance, some form of capacitance, some form of resistance. But if the values of those traces are causing problems, then and they shouldn't be, then we want to address them. And jitter is just, in a nutshell, your voltage or your power supply unit is very noisy, and it's causing the voltage to jitter, basically, and a lot more. So those are the kind of signal integrity issues that might be causing this problem. It's not written in stone, but we'll try to model and understand, how we can solve them one by one. So what I've distilled down the PCB layout design solution is into 4 main topics. One is the general placement. My board over here, I want to have a general placement, because this board is not the best board. It has been malfunctioning for me. As I mentioned, I've been able to make it work, but then it's causing a lot of issues. So how do I generally design a board so that the general placement, general guidelines? So that's how I've divided my PCB layout solution into general placement, then gate drives. So all these MOSFETs will have gate drives, and I don't want them to false trigger. So how should I basically go about designing the traces from the pre-driver, right from say connected to the microcontroller, connected to the pre-driver, and connected to the MOSFET? How should I design the traces? Then we have the high voltage domain, which is basically all the power coming in from your whole high voltage side, which is 7.4 volts to maybe 24 volts. And this is the low voltage side. You're looking at 3.3 volts to 5 volts maximum. So there's a high voltage side over here, and then there's the low voltage side. And then there's a low voltage domain. So if you divide the PCB layout into these 4 categories, I think it gives me a better understanding as to how I want to go about when I'm designing my next PCB and improving on this design, how I'm really going to, focus my design and layout on. So what describes general placements? One of the thing is you want to place all these components on the top side, which I've already done over here. And the whole idea of placing it on the top side is to avoid heat trapping. So if I'm placing on the low side, generally hot air is less denser than cold air, so it will rise. And if it's on the low side, then all the air will basically hit the board, and it will just generate more and more heat. So you're trapping the heat. Whereas in this particular case, if it's on the upper side, then the heat can dissipate more freely. So that's a general placement of making sure that, the components that are generating heat, which could be the pre-driver, the MOSFET, they're all on the upside so that the heat can dissipate freely. You also want to have proper isolation between the high side and low side, between low voltage domain and high voltage domain. And this is the high voltage domain, as I mentioned, and this is the low voltage domain. So you want to have proper isolation. Now, I'm not completely researched as to what real proper isolation means, but I could almost certainly think of that you want to keep all the low voltage and low signals on the one side of the board, and all the high voltage on the other side of the board, which in a nutshell I've actually kind of done in this particular layout as well. I will be talking more about the PCB design of this board shortly through to the CAD software. But for now, I'm just giving the general guideline principles, and then from there we will dwell deeper into it. Another thing is you want to place sufficient ground planes, and you utilize a dedicated ground plane, which I've already done. This is a 4-layer PCB, and then they'll be mentioning more and their ground planes in here. So I've kind of already followed these placement methods. Now let's focus on the gate drive. Now the gate drive is something that I could improve on. In this particular case, I have to reduce the trace length where possible, reduce the inductance. So basically, the traces that are going from the pre-driver right to the MOSFET, some of them are traveling quite a bit of a distance. At least from the PCB standpoint, it's a lot of a distance. It's a big distance, and I might be able to reduce that, or at least figure out ways of making all of them symmetrical at least. I could also increase the trace width, which can help reduce trace impedance. The bigger the width, the less is the resistance, and the less resistance, the better it is. And if I want to reduce the inductance, I could also add resistors in parallel, and there are resistors in series, and you could also add resistors in parallel. And you could also use a straight and simple layout for gate drives. You want to avoid wires, and here there are a couple of wires that are going from one layer to another layer in order for me to connect from the pre-driver to the MOSFET. And the more smaller my board is, and the more denser my board is, the more chance that I would have to use more wires, vias, or however you want to pronounce it. And it's very important during a multi-layer board. And one thing that I could do is also symmetrical gate high and gate low. So that means the trace width of each gate, at least the high side and low side of each, should be very symmetrical. So that when the signal is flowing, it's hitting the gate drive almost at the same time. So that could be some length matching that I could do, which I've not done. Another thing that I've done for this particular design is place sufficient ground planes beneath the gate drive. Use plenty of vias to connect the ground plane. When you say vias, it's more about placing them adjacent to the trace width. And then this is something that I'm not completely understood, but I will probably research in the future. Consider total charge and discharge path of the gate current. So how the gate current is actually charging and how is it discharging? What is the path? Because each of this gate would have some form of a capacitive nature to it, and it would charge and discharge because that's how the gate works. And the whole idea is to figure out how what are you considering the path of charge and discharge, and I definitely haven't. And another principle would be place gate high, gate low resistors near the module connection. So this top is all gate high, and bottom is all gate low in this particular PCB. And near the module connections, reduce sharing heat with pre-drivers. So you want to basically place the resistors near the MOSFET to reduce the sharing heat and avoid it closer to the pre-driver, because this part is heat generating components. That's the reason why it's high side and you want to isolate it. Now let's focus on the high voltage domain. So the high voltage domain is just this area, as you can see. This part will be the low voltage, and this part of the PCB is the high voltage. One of the things that they mention in one of the apps notes that I've been studying, mostly from NXP, from Texas Instruments, and basically accumulated these ideas from different documents that manufacturers provide. And one of them recommendation is place multiple vias near ground pins and connect them to inner ground planes. It prevents heat and provides a low impedance to ground. So as you can see on the top, I put a lot of these wires, and these are connecting the ground planes and the power planes basically. So I've kind of done that, but it could be improved, I think. I have to do some 2D field solver, 3D field solver to really analyze, what's really causing issues with this particular board. And that's something that I will be focusing on in the future of, simulating this board and making and understanding it at a better level, so that before I fabricate it, I kind of at least have a general idea of what to expect. Place high frequency bypass capacitors to VIN and pre-drivers. So this is if there's a high frequency bypass capacitor, place it close to the pre-driver. And these are all the bulk capacitors over here. You want to place them. They can be placed at some distance. This is basically in case if there's some voltage dip or voltage overshoot, tries to balance them. And you can also place some bypass capacitor to prevent some loop inductance near them. and you want to have white traces. So this is all power going into the MOSFET, and I've tried to make all of this white as possible. And the whole idea is to reduce the resistance of the path and the inductance. Then one of the things is to use redundant wires, vias, which I've done over here. Place all filter component as near the device pin as possible. So if this is the device, and if these are the device, there are a lot of filter components right close to it. Place flyback supply filtering as close to the power transformer as possible. So if there's a power transformer powering this, I would have to put some filtering, depending on how you're powering this board. Based on that, I would have to add a filtering capacitor closer to this. Now, this will be on a drone, so how am I going to power this whole thing? And that's something that I would have to consider when I'm actually deploying it onto the main system. There is current sense, so when you're switching and you're spinning the motor, there is current flowing through this, and when we're sensing the current, you want to have an accurate reading. And to do that, there are some few guidelines in the sense that you want to keep your traces as clean as possible, use effective ground shielding, this whole idea so that you can measure the current properly. And you also want to make sure that the trace between the positive resistor and the negative part of the resistor is almost symmetrical, so that you're not and they place close together, so that you're not because if it's a sensitive current measuring sensor, then it will also measure the resistance of the trace, and you want to minimize that. So sometimes they mention just use a 0 ohm resistor in value, because 0 ohm is 0 ohm, whereas your trace might have some resistance. A 0 ohm resistor will not have any resistance, at least ideally it wouldn't. And then you can place pin filter capacitor network near the sensing pin to improve high frequency filtering. So how am I getting this info? As I mentioned, I'm getting them from app notes, data sheets, white papers, studying PCBs from development boards, studying SI and PI from courses, books, and webinar, from Eric Bogerton, from Steve Sandler, from YouTube videos, from Altium Academy, and all those resources that are out there. And some of them are paid, some of them I'm just using the free information that's out there, and a combination of it, and just practicing alone. All these combinations is really I basically invested at least the last month or so in really understanding how I can improve on my design. So now let's go into designing and looking at the actual file. Okay, so what I have over here is let me look into the board that I have right now, which is so this is the board that I have designed. So the board that you see over here is this board. Is this board, and just put in all the layers. So what I have over here is exactly what you're seeing over here. So if I do a 3D model of this, is exactly what you're seeing in here. And as I mentioned, this could use a lot of improvements. And one of the things that I feel that I've not done a good job on is really making the trace widths of the gate drivers are causing a lot of issues. At least I feel that that's where I could really improve on. There's not much symmetry. There are too many wires, and it's not really as clean as I would like it to be. And that's something that in this particular circuit I could actually improve. In order to understand this, this is an NXP P driver, and NXP has given there's a lot of documentation on different ways of developing this board. So I've been studying different boards as well. So one of the boards that I've been studying of lately is this board over here, and this board is something that I just bought from NXP itself, so that I could better understand, just make the software work as well. And that's this board over here. So this board, NXP generally gives you the full working diagram as well of the schematic, so that you can understand it. And what they have done over here, this is one of the circuits, gate driver. Not this one. I think it's power stage. No, not this one. Power stage. Yeah. What they have over here is a little different. They have one MOSFET. So these are bidirectional dual MOSFETs, in the sense they have this complementary effect in here. So this, if you look at this diagram over here, and you look at this, so this is one MOSFET that acts as a high side and a low side. MOSFET configuration. It's a 2-layer board, but it's also much bigger, and that's the reason why it's a 2-layer board, so that they can have the low sides in one side and it's and the high side over here, compared to say
my board, which is significantly smaller, and I'm trying to make it more and more compact. And if I'm using a compact, I can make it more compact by increasing layers. Whereas in this case, they have made it a little bit bigger, but they have reduced the number of layers. So it's a compromise, and they both have pros and cons. But nevertheless, I am writing the software to see how I can make this work, and also understanding how this whole thing works, because I also have the documentation, and I can also measure, I can put my oscilloscope and and measure every single reading as to how this is triggered, and really have a better sense of reverse engineering their boards. So this is one board that I'm really looking forward to get working shortly, and that's how I'm actually improving on my PCB design, is by studying these boards, buying the components, and really measuring based on the oscilloscope readings, multimeter, and just putting my pins, putting my probes in the right place to really understand how things are switching and stuff like that. So that's the next part of where I'm going to progress. Uh, there's another board that's also out there by the GD3000 board. That's something I don't have yet. I may not necessarily buy it. It's not necessary, but it's important for me to study the board, and that's what we have over here. So this is another board that they sell. It's a little is also using the same pre-driver. So in all of these cases, I'm using the same pre-driver. This is the GD3000, and it doesn't matter. And the reason why I'm using the same pre-driver, I'm using the layouts for this particular pre-driver is because I'm working with it, and the schematic is all very similar, so it gives me a better understanding of how to do it. But I think the idea of designing the PCB is still going to be same no matter what pre-driver I use, and this is particularly a BLDC pre-driver. Um, and but tomorrow, if I'm using a Texas Instrument pre-driver, or Infineon, or ST, it doesn't matter. Um, this is just giving me the baseline, so that I can understand based on the component that I'm using, so that it makes the learning much easier. That's really it. So I'm just mostly selecting PCB boards that are using this particular pre-driver, which is the NXP GD3000, for a brushless DC motor. And this is another board as well. So if I do a 3D of this, it's a much more it's a bigger and compact board, and you have to buy a set for this board. As far as I'm concerned, there's a motor driver board, then there's the pre-driver board, and then there's the actual electronics for the board. So the whole kit, I think, costs around $250. I haven't invested into it yet, but it's something that I might consider, just so that I can really understand how the different layouts from a two-layer board, this is a four-layer board, and how I can customize all these design and ideas to make my own custom board that can fit and retrofit this into the quadcopter that I'm building. So yeah, this is really where I'm at right now. In the next few videos, I will be showing you how I'm going to work with this particular board, and get the motor spinning and running, and see if I don't face the same issues as I have done with my custom board, and if there is no issues, then at least I know that I got something to work on. All right, so thank you so much for listening and watching this video. I will be doing a lot more videos on signal integrity and power integrity in the next few months or so, because I'm investing a lot of time really understanding this, and I feel there's a lot of information that I've gained. I'm also taking a course from Eric Bogerton, reading a lot of his books, subscribe to his academy, which is really helping me understand concepts that I've not really I mean, though I've studied electrical engineering, but I've never studied this type of physics before. It's mostly in the power domain side of things. I've never studied things like, what to look for when you're designing a PCB. This was not something that I've ever studied in electric, to a point where it's almost as if it's a new branch of electronics that at least my formal education has not taught me. Something that I wish I did kind of learn. Uh, should have learned, but it was not part of any curriculum. I've dealt with a lot more about the high level principles of how these things work, like timing diagrams, and this, when you go to an electronic course, especially power electronic course, you're just dealing with timing diagrams and understanding the principles and concepts of how these things work. You rarely spend time on actually making this. And I just realized the amount of the science that is required and the knowledge required is clearly a university curriculum in some form or the other, to really make these things work efficiently. And it's kind of sad that we don't do this in electrical engineering. I think now things are changing. So that's the reason why I'm rusty in this, and I'm spending a lot more resources. Of course, I do have a background in electronics, so it helps. But nevertheless, yeah. So that's the reason why in the next few months I'll be doing a lot more videos related to this part of the subject, and then there'll be a little bit of software in the coming months as well, but mostly related to the hardware side of things, as it is important when you're designing drones or designing any robotic system. The electronics is critical, and if you don't understand the electronics, or if your electronics constantly fails, then it's something that you really want to understand why it's failing, and that why is really got me into spending a lot more time into this stuff. So I'm moving a little slowly. It's primarily being because there's a gap in my knowledge, and I want to address it in the best way possible. So next step is to make this work and probe this really well. Another way is to simulate some of my boards and to see, how I can simulate using PSpice, figure out, whether these connections work or not, and try to model this board as closely as possible so that I can simulate them before fabricating. And that's another step in the direction. So I'm reading a little bit more about, how I can simulate these boards using 2D field solvers, 3D field solvers, and better understand my signal integrity issues. And so, having said that, I hope you enjoyed this video or understood, and understanding, how if you want to design a board like this way, what kind of what are the principles you might want to consider before you delve into this. But if you enjoyed this video, do subscribe, like it, and see you next time. Thank you.